for the invitation, and it's wonderful to have so many people here. I'm very excited to talk about what it's like to be a biostatistician. I love what I do, and I want to convey that to you. So I might ramble a little, so if you have questions, interrupt me and let me know if I start rambling too long. So today I'm going to talk a little bit about what biostatistics is, and then who I am and my path to biostatistics. So you heard a little bit about it from Peter. What is a typical day like for a biostatistician? And I'll give you a hint, there's no such thing as a typical day. What types of projects a statistician works on, I'll give you some examples from my own work, and then how you can become a biostatistician too, because everybody wants to become a biostatistician. And then at the end, Mary Carty, who's my colleague from the Department of Epidemiology and Biostatistics, will talk a little bit about Drexel some more and what's so great about our department there. Okay, so almost daily you'll see reports in the popular media about new research findings related to human health. And so I got on CNN.com this morning and pulled up some headlines. Things like, does talcum powder cause cancer? A legal and scientific battle rages. And FDA worried that drug was risky. Now reports of death spark concern. Actually, this article became a homework question for my students after I saw it. And now vaping, now an epidemic among U.S. high school students. All of these are vastly different types of headlines, but all of them have in common that they're the result of the work of a multidisciplinary team, including biostatisticians. Biostatistics is the application of statistics to a wide range of topics in biology, medicine, and public health. So it requires a broad skill set, including math, so having some math background is really important, an understanding of computers and computer science, and some interest in biological applications. So a lot of times people will ask me, I'm a math major, I've never had any biology, can I be a biostatistician? Biostatistics isn't necessarily biology, the statistics of biology. It's the application of statistics to biological and biomedical fields. So most people who get degrees in biostatistics come from math backgrounds but have interest in the applications that you can use math for. Biostatisticians play essential roles in designing studies and analyzing data from research problems. So a lot of times people say to me, oh, do you mostly deal with data? But the reality is I mostly deal with people. I spend a lot of time talking to people about how to do research effectively, how to set up their research design so that when I do get the data, my job is really easy. There are a lot of different ways biostatisticians get involved in research, formulating scientific questions to be answered. So that sounds like the job of the scientist, the lab scientist, or the clinician. And scientists have great ideas for research, but they don't always translate well into questions they can answer. And so biostatisticians help them translate their science into answerable questions. Determining the appropriate sampling techniques, who am I going to study, is really important. How you decide that and how you choose that is really important to being able, again, to analyze the data and have good results from that. I do a lot of work on coordinating data collection procedures. So I run coordinating centers, and that's exactly what I do, is work with clinical staff and clinical scientists to understand how to get their data from the patient or the subject to me for analyses. And what is the process by which that's done? And I'll talk more about all of these. And then, of course, I do actually carry out statistical analyses to help answer these questions. I also do work to develop new statistical methods. And so what makes a biostatistician distinct from other fields where analysis is done is that biostatisticians do methodological work. So I develop new methods for understanding research in clinical trials. So as Peter mentioned, I do work to look at if you have multiple outcomes in a clinical trial, how does that impact your answer? Or if you look at your data multiple times throughout your study, how does that impact your answer? So how did I get here? So I was a math major at the University of Kansas. I kind of fell into being a math major. I started off pre-law and thought I was going to be a business major, and I took an economics class and couldn't stay awake for it. So I scrapped that, and I kind of wandered around a little bit, and during my second year, I realized I kept taking math just for fun. So decided to be a math major. And so that was my first stop, was the University of Kansas. And then as I got towards the end of my junior year, people started asking me what I was going to do when I graduated, and I didn't know. And then I was just having this conversation a few minutes ago, people kept saying, are you going to be an actuary? And I didn't know what an actuary was. So I said no because I didn't know what it was. And when I looked into it, with all due respect to anyone who wants to be an actuary, it seemed kind of boring to me. And if you don't know, an actuary is a person who helps determine life tables for insurance companies. So basically, you're taking information about people and figuring out how long they're going to live. That didn't seem very exciting to me. So I went to the library, and at the time, there wasn't this thing called the internet, so I got a book. That's this thing that's about this big, and it's got a spine, and you open it, it has pages. And so I got this book called Peterson's Guide to Graduate Studies. And I said, okay, I want to do something that's quantitative, but I don't want to get a PhD in math, and I don't want to have to take the math GRE subject test, and I don't have to have a foreign language in my PhD. So I started flipping through, and I came across biostatistics. And I was like, well, I'm a math major, I have a biology minor. This seems like it might be a good fit for me. So I really kind of stumbled into it. And the next year, I found myself at the University of Iowa getting a master's in preventive medicine and environmental health, but a specialization in biostatistics. And I found the right thing for me. I was really, really lucky. I found that it combined my quantitative skills with my desire to interact with people and data. And so 2 years later, I found myself at the University of Michigan, which is where I met Peter, and I got my PhD in biostatistics there. And again, I found, so why I got a PhD, I should say, for a short amount of time, I was a math education major. And I started taking education classes and realized that I did not want to teach high school math. I wanted to do more than that. And so I decided I wanted to get a PhD eventually. And so that's why I kept going for my PhD, was because I love to teach and I enjoy engaging with students, and I wanted to have the opportunity to teach as well. And so after 7 years at the University of Michigan, I had a baby and a lot of intramural champion t-shirts. It was time to move on with my life. So I went to the University of Alabama at Birmingham, where I spent 11 years as in the Department of Biostatistics there. And had a great time, got involved in some amazing research, and had the opportunity to work with students in a lot of different venues. I was the director of the graduate program for a while. So really got a chance to do the things I loved. And I had a great time there, but the time came for me to move on to do something else, and the opportunity came up. So I decided to move from one institution with a dragon mascot to the other one, and that's how I found myself at Drexel almost 3 years ago now, and it's been a great decision. So that's kind of my path. So it's not always well planned. It's not always, I didn't know from the time I started college that I wanted to be a biostatistician. It wasn't that well planned. Some of it was kind of falling into the right thing at the right time, or taking a leap and making it across that valley. So, but I will say I love what I do, and I'm really happy that I am where I am. So what do I do in a typical day? I do a lot of different things. So on a typical day, you might walk into my office and find me writing a paper or reviewing a paper or reading a paper. You'll find me sitting at my desk doing analyses. You might find me teaching. I'm in the classroom, and I spend a lot of time in the classroom. Some people tell me I spend too much time in the classroom, but I love it, and I find it is an important thing to do. I spend a lot of time in meetings. Different types of meetings. Some meetings are more fun than other meetings. I had a meeting this morning before I came out here where I got to talk about some cool research I'm doing, where we're trying to understand the community factors that influence risk of diabetes, so that was fun. But tomorrow I have some meetings where I have to talk to people about what they're going to be doing next year. It's not quite as much fun. And then finally, some mentoring. I do a lot of mentoring as well. I work with several students in different capacities to help them become what they want to be. But no 2 days are the same, and it's what I really love about my job. I think if you ask your faculty in here at Ursinus, they'll tell you the same thing, that every day is different. They get a little bit of a lot of different things. And it makes it really, really fun to do what you do. Okay, so I have to tell you though that my alter ego is Stat Girl. I'm Stat Girl. So this is me at Halloween a few years back. These are all scientific posters that were turned into my Halloween costume. I'm extremely proud of this because I'm not a very creative person, and so to be able to do something creative. I also have a blog, that's Stat Girl blog, if you're interested, and I'm on Twitter at StatGirlLAM. Okay, so anyway, what do I do? What are real problems that biostatisticians work on? So I'm going to give you some background. So most of what biostatisticians do arise from real science, as opposed to developing statistical methods because they're beautiful, which has merit in and of itself. The problems I work on arise from real data. So I'm going to give you some background about the research I'm doing. According to the Centers for Disease Control, stroke was and still is the 5th leading cause of death in the United States. Stroke's the #1 cause of serious long-term disability in the United States. And because of that, it's an extremely expensive disorder. We spend a lot of money, it costs a lot of money for lost days of work, for caretaking, for rehabilitation from stroke. And about 1/3 of stroke survivors will have another stroke within 5 years, and about 14% will have another within 1 year. So stroke is an extremely debilitating disease that happens frequently, big killer. Recurrent stroke or second strokes or subsequent strokes are also really important and really hard to prevent. So understanding how to prevent stroke is extremely important. But it's really hard to do studies to understand how to prevent a first stroke because although we all probably know somebody who's had a stroke, stroke's a relatively rare event. So if I wanted to study stroke, I'd have to have a really, really large sample to do that. And so a lot of stroke research occurs on people who have already had a stroke because now we have a really nice subset of people that we can then go study and learn about other strokes. And so understanding how to prevent recurrent strokes among stroke survivors is also a topic of a lot of research. So one thing we know is that blood pressure medication is a good way to prevent stroke, or to lower blood pressure, which is related to stroke. Okay, so if somebody has high blood pressure, they're more likely to have a stroke. So if we can lower their blood pressure, then we might make inroads in preventing strokes or subsequent strokes. Also, we know that lifestyle modifications are important, such as diet, healthy diet, exercise, and not smoking. So all of these, poor diet, lack of exercise, and smoking all contribute to risk of stroke. We also know that some antiplatelet medicines like aspirin or clopidogrel, Plavix, will prevent strokes. On average, stroke mortality is 20% higher in the southeastern part of the US. So people who live in this part of the country have a higher risk of stroke than people who live elsewhere in the country. There's this little area, this is called the stroke belt. There's this little area along the coastal plains of North Carolina, South Carolina, and Georgia. It's called the buckle of the stroke belt. People who live there have a 40% higher risk of stroke than people who live in the rest of the country. Okay, so that's substantial. Further, we know that African Americans have a 40% higher risk of stroke than whites. So stroke disparities are also a big issue in our country. So I'm going to talk about 2 different studies today that I've been involved with. The first is the Secondary Prevention of Small Subcortical Strokes, or SPS-3 study. This is a randomized clinical trial to determine what might help prevent a second stroke in patients who already had a first stroke. And I'll define these terms for you in a second. The second is called the Reasons for Geographic and Racial Differences in Stroke, or REGARD study. And this is a longitudinal cohort study to help understand why there are regional and racial disparities or differences in stroke. So these are 2 different types of studies. This one is a clinical trial where we have 2 treatments and we're following people to see which treatment is more effective. This is an epidemiologic cohort study where we have a group of people and we're watching them over time to see what happens. Okay, and so I'm going to talk about both of those today. Okay, so SPS-3 is a multi-center, multinational, randomized clinical trial. And again, I'll define these terms in a second, with 2 main goals. The first is to understand, do stroke patients who received aspirin have fewer second strokes than stroke patients who received aspirin and Plavix or clopidogrel? So Plavix is the brand name, clopidogrel is the generic name. The second question was to try to understand whether stroke patients whose blood pressure is lower to 130 to 149 millimeters of mercury have fewer strokes than patients whose blood pressure is lowered even further. Okay, so the reason these came about is because there's some evidence that having 2 antiplatelet therapies is better than 1, and because there's some evidence, because we know that lowering blood pressure in this range is effective for helping to prevent people from having stroke. So what if we go even lower? Is lower better? And we didn't know the answers to these questions when this study was designed. Okay, so I said this is a multi-center study, so that's just what it sounds like. The patients for the study come from multiple medical practices around the country, and in fact around the world, and I'll show you that in a minute. Multinational, it comes from multiple countries. And randomized means that the treatments are determined by random assignment, that we essentially flip a coin. And if it's heads, you go in one group, and if it's tails, you go in the other. Okay? And so I don't know when a patient comes into my clinic what treatment they're going to be in. Okay? And in fact, this was blinded. So the patients didn't know if they were getting aspirin and Plavix or just aspirin, because they would get a placebo. So they don't know what treatment they're getting, and I don't know what treatment they're getting, so that I don't make judgment about their health based on what I think their treatment is. So it eliminates biases. Okay, so this is the location of our patients in SPS3. So we were looking at primarily patients from North America, Mexico, South America, and Spain. Okay, so it was primarily English and Spanish speaking participants with a few French Canadians sprinkled in here and there. Okay, so that's one study I've worked on. The other is the REGARD study, the Reasons for Geographic and Racial Differences in Stroke study. And the goals of this study are to determine why Southerners die at higher rates from stroke than their Northern counterparts, and why African Americans die at higher rates from stroke than their white counterparts. So as I mentioned, this is a cohort study. It's a longitudinal study where we collected data on a bunch of people, 30,239, and we watched them going forward to see who had strokes. And then we knew a lot about them. We collected a lot of information about them. We collected dietary data. We collected health risk factors, their height, their weight, their blood pressure. We collected all the medications they were taking. We know where they live, so we know about their neighborhood. And then we've been following them. We're still following them. This started in 2003. And so we've been following them now to see who has strokes, and then to see what information we collected might be related to having a stroke. And so that if we can understand what might contribute to these disparities, then maybe we can act on that. Then maybe we can develop policies that help change those parameters. Or we can implement trials, or we can implement new treatments to help change those risk factors. So this figure shows the REGARDS participants. It took us 5 years to enroll them all in the study. There's 30,000 of them. The red dots are white participants, and the blue dots are African American participants. And what you see is we have a lot more people in the Southeast because we oversampled. We got a lot more people there because we wanted to be able to make some statements about the folks who live in the Southeast. Otherwise, what you see is participants are where people live. Right, so I'm from Kansas, and you can see here's the Kansas City area, here's Wichita, and then there's a few rural people. In Nevada, you can see down here we have a few people down where Las Vegas is, and then Nevada's pretty rural. So our participants come from all over the country, all over the continental U.S., and they reflect where people live in the United States. Okay, so I'm going to take a divergence to talk a little bit about what I might do on a typical day in a research study such as one of these. Okay, so first, this is data management. So this whole wheel here represents different aspects of data management. And so I might be involved in capturing data first, right? So we have to get data from the participant or the patient to the analyst. And we have different ways we might do that. I have a collaborator in Alabama who's interested in understanding if we can teach children to cross the street safely using a virtual reality environment, right? So we can't take kids out to the crosswalk and say, cross and let's see if you get hit. That's not ethical. But we can do that in a virtual environment. They can wear a virtual reality, they can be immersed in a virtual reality environment and virtually step into a street and virtually get hit by a car. And we can see how often that happens and whether they're learning. And so, but in this study, it's a relatively small study, just a couple hundred kids. So they collect data in an Excel spreadsheet and send it to me that way. In the Regard study, we had a lot of different mechanisms for capturing data. We had a computer-assisted telephone interview where we had interviewers who were on the phone and they would type into the system the answers as the participant told them. All of that required programming, not by me, by computer scientists who spent time developing this system so that our interviewer could call someone on the phone and the interview questions would pop up on the screen and they would answer them as they go along. In SPS3, we had a system where each of the sites, the coordinator, the study coordinator, the research coordinator, would log into a website and it would bring up what looked like their data collection form. And they would enter it and it would get uploaded to our servers. So every different type of study could have a different way of collecting and capturing data. And so I have to work with the computer scientists, the programmers, and with the clinicians to make sure that we have a system that's flexible enough to meet the needs of the clinicians, but also meets my needs statistically, so that when the data come out of there, they make sense to me. Okay, so that's a big part of what I do. Once I have those data, I have to validate them and verify them. So I have to make sure that they're valid, that somebody in my study isn't -5 years old, and that someone in my study of children isn't 90 years old, right? And then I have to make sure that they're actually correct. So I work on validation. We create validation rules sometimes. Sometimes I look at distributions and look at ranges to make sure things are in the right ranges. And then we work on verification. So I work with the individual sites. They send me their data forms, and we enter them at our site, and we make sure they match up. Okay? Data cleansing or data cleaning. So if you haven't worked on real data before, when you do, you'll find that it's never clean. It's never looks like you think it should, even if the researcher thinks it is. So I might get a file from my collaborator who's working on the virtual reality, and he'll have child's gender, and it will say male, MF, capital M, capital F, capital M, capital F, male, lowercase f. So I may have to go through and make sure that all of my variables are coded the same way. I may have some missing data. I may have to ask why there aren't values in those cells. Okay, so making sure the data are clean. We may have to move data around. So I talked about this Diabetes in Communities project that I'm working on, where we're trying to understand what community level factors influence risk of diabetes. There are 4 sites working on this, and we're the data coordinating center. So we have data that we're going to be sharing with 3 sites around the country, and so we may have to move this data around. And finally, we may have to do other things to the data to enrich it. So in the Diabetes in Communities study, we are collecting a lot, or we are downloading really a lot of data that's external to the study participants. So we're getting on the census website and we're bringing in census data so we can understand census level variables such as neighborhood poverty or percent women head of household, or there's tons of census variables. Or we might be downloading data from the EPA about the environment, trying to understand in different communities how much particulate matter you're exposed to when you're breathing. So all of these are aspects of data management that I'm involved in. That's not statistical. And frankly, it's not something we teach a lot of or do a good job of teaching in graduate school. A lot of this comes from on-the-job training. Although we try. Okay, so what else do I do? Well, remember I said that the clinical site coordinator will bring up her or his screen, and it will have the data entry form. I have to help develop those case report forms. So how do they collect the data? And that's important because I want to make sure that if they're collecting age, we do it in a standardized way. So either I want them to collect birth date or I want them to collect age. I don't want them to collect both. Why not? Any ideas? Yeah.
You could look at the data later and the kid would be older than they were at the time where the data was collected.
that is a true statement, but that's not why I don't want them to put both on the form. So what if they make an error on one and they don't agree? Now what do I use? So at least if I only collect one, if they make an error, I don't know. So I don't want them to have opportunities to disagree across forms. So if I have a birth date on one form, I want it to automatically populate on another form so that I don't have discrepancies across my forms. Or if they have to enter it multiple times, then I want something to pop up and say, no, you said that person's birthday was January 1st, 2015. Now you're saying it's 2016, which is it? Okay, I don't want to get data from two different forms that has conflicting results on it. There are other reasons why it's important for a statistician to have input into developing case report forms. And a lot of that has to do with, I'm the person who's going to analyze the data. So I want to understand how they're collecting it. Okay, so then I have to ensure they're actually entering their data into the system. So how do I do that? Well, I pay them, right? Frankly, if they're collecting data for a study, they don't get paid until those data are entered into the system. Oops. Okay. I sort of say that tongue-in-cheek. It's true. We do pay the sites to enter their data. But there are other things we can do as well. And so we do a lot of reporting to check who's supposed to have data entered and doesn't, and that sort of thing. I mentioned checking the quality of the data already and moving data from place to place. Once I have the data, I have to create data sets that are analyzable. So for instance, if they did put birth date, now I have to calculate age so that I can use age in my analysis. If they had blood pressure, I may want to create a variable that's hypertension as opposed to blood pressure. So I have to create data sets that include the right forms of the variables for me to use in my analysis. All right, so what else do I do in a research study? So I create pretty graphs, right? So I plan sample size estimates using measures of uncertainty. So what does that mean? So remember I said that if you want to study stroke, that it's a fairly rare event. So you need a lot of people to do that, right? So you have to have a very large sample size. Well, the regard study has 30,000 people because we wanted to study first strokes. And so in order to have enough people to be able to make statistical statements, bless you, about differences between groups, we had to collect 30,000 people. Now 30,000 is really large, and it's not because we just wanted to say there were differences between northerners and southerners. What I didn't tell you is, in addition to African Americans being at higher risk and southerners being at higher risk, African Americans who live in the South are even higher risk yet. So that's an interaction. We wanted to look at how those two interact. And in order to do that, we needed to have 30,000 people because stroke is a rare event. Okay? If it was a more common event, if it happened more frequently, if I was looking at heart attacks, I wouldn't need quite so many people. I mentioned data cleaning. I spend a lot of time cleaning data, The most important thing I do is descriptive analysis. So what do the data look like? I tell my students they should never be surprised by the results of analysis. You should always know when you go into the analysis what you're going to see at the end based on what your data look like. So what does that mean? I do a lot of plots and frequencies to see, I want to look for outliers, I want to look for strange values, and I want to look at how things are related to each other. Okay? And so that's the most important step in analyzing data, is doing descriptive analyses and trying to understand what the data look like. I hope that when you're taking your statistics classes, I'm reinforcing what you're learning, not contradicting it. And then I perform confirmatory analyses. Can we answer our question of interest based on our data? Or what is the answer to our question of interest based on our data? And the methods I use to analyze the data depend on the question, the complexity of the data. Okay, so a lot of what I do is trying to understand what the most appropriate approach is to answer the question. Another thing I like to tell my students is there's never one answer. There's never one correct way to analyze data. And this is a really frustrating concept for students, especially with math backgrounds where a lot of the time there's an answer to a math question and there's usually a single answer. So I always say if you go to the Biostatistics department and you start knocking on the doors, different faculty, and you ask them, how would you analyze these data, you might get a different answer from everyone and behind every door. But hopefully you'll get the same conclusion. So there's all these different methods, but the goal is to ensure that we get the same conclusion. And so it's a hard idea, especially for someone like me who's a little bit type A and likes to have everything in order, that there isn't always one answer. So I spend a lot of time trying to figure out what the best way to answer the question is before I start to do it. And the best way I would answer the question may not be the best way one of you would. After we get our answer to our primary question of interest, then we might do some exploratory analyses. So are there other questions that we should be asking? And that doesn't mean are there questions we should be asking in our current data, but maybe our current data can help inform new questions. And that's really what science is. This is that perpetuation of scientific questions. Okay, so sometimes we take different approaches when we do exploratory analyses, but it's still helping us generate new hypotheses for research. And then I develop new methods to help answer questions that can't be answered with existing methods. So what does that really mean? So I might be meeting with a collaborator and they say, I want to do this sample size re-estimation in my clinical trial. Can I do that? And I'll say, I don't know. Let me look at what the statistical properties of this method will be, and we'll see if that is going to give you any problems, any errors, or cause you to say that there's a difference when maybe there isn't. Okay, so I might go back to my office and spend a few days, weeks, months, depending on the problem, trying to solve this problem, answer this question in a way that I can convey to my collaborator. Or another issue might come up where perhaps we have two outcomes. Maybe we're looking at, so I'll give you the example from my dissertation. It was a study of pelvic organ prolapse, and there were two outcomes, quality of life and pain and sexual function, and there was the treatment could cause them to go in different directions. So one might improve sexual function but have increased pain. And conversely, if pain decreases, then sexual function might decrease. And so the two outcomes aren't going in the right direction. Ideally, you would have less pain and better sexual function, right? So there wasn't good statistical methods out there to analyze this data when you have this kind of disparity, and they're related to each other, they're correlated. So my dissertation project was to try to figure out how to answer this question in a way that we could get answers that made sense in terms of both outcomes. So that's how I develop new methods. But every time I've ever done anything methodological, it's always come up as I've been meeting with a collaborator or I've been working on a study, and this question, I'm not satisfied with the methods I have to answer this question. So it's always motivated by a real data problem. Okay, so you might find me at my computer. A lot of days you find me at my computer. And what am I doing at my computer? I may be writing reports to investigators. So I have to tell my collaborator what results I found. And I have to be able to do that without saying that I fit a quantile regression and this and that. They don't understand, they may not understand that. So I have to be able to convey the results of my analysis in a way that makes sense to them. And that's not an easy skill. Hopefully it's a skill that you're working on now by writing in all of your classes. But it's definitely a skill that most graduate programs also try to teach. And it's not an easy skill. And some people are better at it than others. I help write manuscripts. So I have a lot of papers that I've worked on throughout my career that range from more statistical methodology to these problems in stroke and the environment. And I play a key role as a statistician in writing those. So how many of you have read scientific papers or medical papers? So if you think about how they're structured, good, then you'll know that there's this methods section. And depending on what the context is, it might be laboratory methods, or it might be statistical methods. And the person who usually writes that is the person who works in the lab or does the statistics. So I have to be able to write that for this journal audience. And that journal may be in pediatrics, or it may be in epidemiology or injury prevention. So I have to be able to write it in a way that's accessible to non-statisticians. And I think that's really fun. I think one of the bigger challenges of my job is trying to teach my collaborators about statistics while learning about what they do. I also, because of our laws, I have to create data sets for public use. So a lot of what I do for my research is funded by the government, either through the National Institutes of Health or by the Centers for Disease Control, or by NASA, actually. I had some funding from NASA. And whenever you collect data that is funded by the federal government, you have to make that available for public use. And that's not easy, because if I collect data on each of you, I probably know something about you individually that distinguishes you, whether that's your name or your address or your birth date or your social security number. But when I create a data set for public use, none of that can be in there. Okay, so I have to make sure I create this data set in a way that masks any data that's called protected health information. So anything that might be related to you as an individual. Maybe you come from a very rural town and there's only 5 people in that town who are your age, sex, and ethnicity. Then I can't even include you in the data set at all. So I have to pay close attention to who's in my data set and how they're described. So that's a very quick summary of the different tasks that I might do as a statistician. So I'm going to go back to my examples now and tell you about, now, what did I do in those studies? Okay, so besides all of those things, I analyzed the data for the results. And so this is SPS3. This is, remember, the clinical trial where we are looking at whether one antiplatelet therapy alone is better than 2. And the goal was to prevent recurrent stroke. And so what's in this plot is, on the x-axis, this is the time since randomization. So how long was somebody in the study? And you can see that we had 3,000 people, 30-20, who were enrolled in the study, and we had 8 people who made it to 8 years. And most people were in this 2, 3, 4 range. It's where you start seeing people drop out. And the y-axis is the probability of a primary event, or having a stroke. And so what I'm looking at here is this red line shows me the probability of having a secondary stroke, second stroke, if you're in the aspirin and placebo group, so only get one antiplatelet therapy. And this black line shows me the probability of having a second stroke if you're in the aspirin and clopidogrel group, if you had 2 antiplatelet therapies. So just based on this figure, do you think there's any difference between these treatments? Do these lines look like they're different to you? No, right? So what we found was there's no difference. And we express that as what's called a hazard ratio. That hazard ratio tells me the ratio of the likelihood of having a stroke in one group to the other. So if it's a ratio and there's no difference, what would I expect that ratio to be? 1. So the closer this hazard ratio is to 1, the further it is from 1, the more likely it is there's a difference. And so what we found, was that it was 0.92, and this confidence interval tells me how much variability around this, how certain I am that that estimate is close to the real value. And our confidence interval, if that includes 1, then that tells me that this isn't any different than 1. Okay? So what we found was there was no difference between these 2 treatments. But I didn't need to do this to see that. I could have just looked at my data, right? My data showed me that. These lines overlap up until about here, but then I don't really have any people out there. Okay, so I look at my data and see that. Okay, well this one's a little deceiving. This is the blood pressure control arm. And so similar figure. Now we still have time since randomization, and we have the probability of a primary event. You can see that it's all swished down below here. So it's a little bit deceiving. You can't see these 2 lines quite as well. But the red line is our lower blood pressure group. And the black line is our higher blood pressure group. And so looking at this, it's a little harder to tell. Excuse me. I think if I spread this out a little bit, those lines might separate a little bit. So it's a little deceiving. They're not completely overlapping, but they're pretty close, right? So if I look at this picture, again, I would think, there's probably not a difference. What we found was that the hazard ratio was 0.81. So the risk of having a stroke was about 20% lower for people in the lower blood pressure group than in the higher blood pressure group. So there was some benefit, but my confidence interval still overlapped 1. So it wasn't statistically significant. There's too much wiggle room around that estimate for me to be able to say with certainty that there's a difference between these groups. This one was a little bit harder because it is close, but not quite there. Okay, so just to give you a little bit of a biological application, one of the things that came out of that study was, or one of the things that's been known was that there are inherited factors that may influence how some people respond to antiplatelet agents. So specifically clopidogrel, right? So there's a gene that they call the clopidogrel gene because those who have it might respond more favorably to clopidogrel than others. It's a reduced metabolism of cytochrome P2C19, and it's known to increase clopidogrel resistance. Okay, so we had some colleagues who wanted to see if there was maybe a genetic reason why we didn't see a difference. Maybe we didn't have people who were responding the right way based on their genetics. And further, just in a broad sense, it's possible that there are genes that play a role in who gets a stroke. So we had a sub-study called the SPS3 gene study, in which a subgroup of our patients provided saliva for this study. So we had people come in, they spit into a tube, and we sent it off to Florida. And in Florida, they analyzed the genetic composition of our spit, and they genotyped this CYP2C19 gene among some others, and they wanted to know whether those who had certain variants of these genes had an effect for the treatment. So maybe in this subset who had the certain variants of this gene, the treatment worked, even though it didn't in the whole group. Okay? No difference. Didn't matter. The genes didn't matter either. We also included our samples in a genome-wide association study. So they looked at every gene in the genome, combined with other people from other studies to try to see if they could identify genes that were associated with stroke. And that's still ongoing. This takes a long time because they have to get all this information from a whole bunch of different studies. And moving data around is not easy. So, and my guess is that they'll find a couple genes, but then they won't be able to replicate them. Because that's what happens a lot of times in these genomic studies. But so this is a more biological application. Where I was involved in this analysis, even though I'm not a geneticist, and I don't have even really a good knowledge of genetics. I've taken some genetics, but I have the tools to do the statistics. And my collaborators were able to help me understand why the methods I was using were the correct methods to apply to that problem. Okay, so a little bit disappointing, right? So this study went on for a long time, 10 years, and we didn't find any differences in our treatments, and we didn't find that the genes made any difference. So what? So what good was it? Well, it is still a contribution to science. We still found, now we know that it's not necessarily effective to use those two treatments together. And in fact, we had some safety issues. So we know, in fact, that it's not just not effective, but it maybe is harmful. Okay, so the REGARD study has published many, many papers now that examine stroke risk factors, and have a variety of results. So one of the things we found is that there are racial differences in blood pressure and hypertension. But we found that African Americans are just as likely as whites to know they're hypertensive and to be treated for their hypertension, but that the control of their hypertension is not as good. So this could be a potential risk factor for stroke disparities. So there's disparity in hypertension control, which could lead to disparity in stroke risk. We found that different medications are being prescribed regionally. And perhaps that may have something to do with these regional differences in stroke. We also have found, of course, that aging is a risk factor for stroke, but that this risk for blacks and whites differs across the age spectrum. So at young ages, African Americans are much more likely to have a stroke than whites. But at about age 70, that risk comes back together, and then at older ages, whites are much more likely to have a stroke than African Americans. So these racial differences that we see are not constant across age spectrum. So that helps us. That helps give us targets at which age groups we should be studying to try to understand these disparities better. Okay, so what about regional differences? And again, a variety of results. So whenever we interview people, they always, especially in the South, they say, we know why Southerners have more strokes, because we eat so much fried food and that's bad. Well, the reality is dietary patterns do make a difference. That people who eat healthier diets have lower risk of stroke. But we haven't found that that's a regional thing. We haven't found that that impacts regional differences in stroke necessarily. We also think about the environment. So this is something I'm particularly interested in, is how what we breathe might impact our risk for stroke. So again, this is something that's very clear if you're studying respiratory disease, but when you're studying stroke, maybe not quite so clear. But again, we found that while what you breathe impacts your risk for stroke, it doesn't vary regionally. We did find that sunlight exposure also impacts your risk for stroke. So, and we're not exactly sure what the mechanism is for that. Could be vitamin D. But again, it doesn't vary regionally. We've had a really difficult time trying to understand what might explain these regional differences in stroke. Okay, so I'm going to switch gears and talk about what to do if you want to be a biostatistician. So any questions about the research aspects or these results, or what the role I played in them was? Okay, so currently, and this is true for the last 20 years, and it's going to be true for the next 20 years, there is a shortage of good biostatisticians, and analytic skills are in high demand. Okay? There are outstanding job prospects for biostatistics graduates at the master's and doctoral level. You can find jobs in academics, so you can, if you have a PhD, you can do what we do. You can be in a classroom. Primarily, you can primarily do research and everything in between. If you have a master's degree, you can work on research studies that are being carried out at an academic institution or in a medical center. You can go to industry. You're just down the street from GSK and Pfizer. There's lots of biostatisticians that are in industry, both at master's and doctoral level. You can work for the government. You can work for the CDC or the National Institutes of Health, the FDA or the EPA or the Forest Service. There are endless possibilities. You can work for nonprofit organizations. The RAND Corporation does an amazing amount of research, and it's a nonprofit. So there's tons of jobs. And it is the top job, again. In 2018, Forbes named biostatistics as the #1 top job for master's degrees and statistics as the #2. Okay, and this is just not a new phenomenon. 2017 U.S. News and World Report said statistician is the #1 business job, the #2 best STEM job, and the #6 in the top 100 jobs. Okay? In 2016, Forbes said statistics and biostatistics again were the top 2 master's degrees for jobs. And the Bureau of Labor Statistics in 2015 projected statistician as one of the top 10 fastest growing careers. This is something that is happening and not going anywhere. Okay? So what do you do if you want to be a biostatistician? So one thing you can do is go to a summer institute in biostatistics. So these are programs that the NIH sponsors that are at 6 institutions currently: Boston University, North Carolina State, Emory University, University of Iowa, University of Minnesota, and University of Colorado at Denver. And each one is slightly different. You spend 6 weeks doing this program, you live there, you get to know your classmates, and you learn a lot about, some of you have done it, right? So And you can go live somewhere fun for a summer. So maybe you love the Northeast. It might be a great opportunity to go live in Atlanta and enjoy the heat and humidity for 6 weeks. Or maybe you hate humidity, you can go out to Denver where there's none. So it's a great opportunity. These programs are phenomenal, and they will help you decide if you do or don't want to go into biostatistics or epidemiology as well. Okay, so I have to put in a plug for SAMC, the Statistics and Applied Mathematical Sciences Institute. This is located in Research Triangle Park, North Carolina, and it's a joint venture by Duke, NC State, and UNC, and they have undergraduate workshops in mathematics and modeling 3 times a year. So if you go to samc.info, there's information about it, and you can learn about those. Also, research experiences for undergrads. The Math Alliance, which I'm not going to talk about today, has a great resource. Let's see if I can get to it. I'll put it up at the end of the talk because it might be easier to do that. But there are resources out there for research opportunities. So all different types. The Summer Institute programs are different than the research opportunities. And they're all different types. And these include a lot of math REUs as well. So if you're less interested in math and more interested, or less interested in biostatistics and more interested in math, then there's a lot of opportunities here. Okay, so I mentioned this earlier, but if you want to go into biostatistics, you don't have to have a biology background. What we look for on applications is 3 semesters of calculus and a course in linear algebra. So if you're a math major, you probably already have that. Strong GRE scores, and letters of reference, and your statement of purpose. And this is for our master's degree, but also coming soon is our PhD program, which will be starting next fall. So the entry criteria will be the same.
Fall 2018.
Fall of 2018, yes, this fall, soon. Okay, so do you want more information? Are you excited? You can contact me at this email address, or Mary is going to give you a few minutes about Drexel as a whole. She's here. Our school has open houses that you can attend. Right now, I think the next one's not till the fall, but you can get on the website. And the graduate school at Drexel, the graduate college, also has open houses, which we participate in. And then finally, some references and another photo. I like to end with what's really important, and that is my time with my family. This was 2 weeks ago. We were backpacking in the Grand Canyon. And now I'm here and not backpacking, but it was an amazing trip, and it's really important that you remember that whatever you do in life, it's important to have balance. So I'm going to turn it over to Mary to just say a few words, but thank you very much for your time.
Thanks everyone, you guys are a great audience. So you probably know Drexel, we're in downtown Philadelphia. Some of you have already applied, some of you are going to be starting in the fall. We have all sorts of graduate degrees. We have Masters of Science.